Hey everyone, ready to explore some quantum mechanics. Today we're going to be tackling something pretty crucial to how physicists make predictions in a world where things get a little fuzzy, shall we say. We're talking about expectation values.
It's a really interesting concept, and it actually highlights one of the key differences between the quantum world and the everyday world. Like, think about classical physics. If you throw a ball, you can pretty accurately predict its trajectory, right?
Yeah, for sure.
But in the quantum realm, it's not like that. It's not about certainty. It's all about probabilities.
It's so wild to think that at the tiniest level, it's not clear-cut. So where do we even begin if we can't pinpoint a particle's position or how it's moving?
Right. Well, that's where these things called wave functions come in.
Mm.
So each particle you see is described by a wave function, which gives us like the probability of finding it in different locations. Imagine it like a map of possibilities instead of a fixed point.
Okay, so I'm picturing a fuzzy cloud where the particle could be anywhere within that cloud, and the thicker the cloud, the more likely it is the particle is there.
Exactly. It's not that the particle is like literally spread out, but rather its position is just uncertain until we measure it.
Oh,
And it's the wave function that tells us like how likely it is we'll find it in different spots when we take that measurement.
so if we can't know for sure where a particle is, how do we even start to predict its behavior?
That is where the concept of expectation values comes in. So it's not about measuring one single particle over and over. Imagine instead you had a bunch of particles, all prepared in the exact same state. The expectation value is, well, it's sort of like the average outcome you'd get if you measured the position of all those particles at the same time.
Oh, I see. So instead of trying to predict the behavior of one particle, we're shifting to understanding how a whole bunch of them behave statistically.
That's a great way to put it. And it's this shift in thinking that lets us make actual predictions from a system that, at its core, is all about probability?
That's starting to make sense. But can you give us a more concrete example of how this works?
Sure. Let's say we've got a row of bottles, right? And each bottle's got a particle, all in the same state. Now imagine you've got a bunch of grad students, each one gets a bottle, and on a signal, they all measure the positions of their particles and write down what they find.
I'm picturing a very chaotic lab right now.
Right. But it's organized chaos because if we plot all those measurements on a histogram, you start to see a pattern. And that pattern reflects the probability distribution described by the wave function. And if we take the average of all those measurements, we get close to the expectation value of the particle's position.
So we're crowdsourcing the measurement to get a sense of the overall behavior. But how do we actually calculate expectation values with math? I feel like this might involve some serious number crunching.
It does involve a bit of calculus, but the idea is elegant. We use what some people call the sandwich method. So you take the operator that represents the quantity we're interested in, like position, and you sandwich it between the wave function and its complex conjugate.
Wait, hold on. Complex conjugate, that sounds kind of intimidating.
It's not as scary as it sounds, I promise. Think of it like a mathematical mirror image of the wave function. And we need it to make sure that the final result we get is a real number, something that we can measure.
Okay, I'll trust you on that one. So we sandwich the operator between the wave function and its complex conjugate. Then what?
Then we integrate over all possible positions. So we're basically adding up the contribution from every possible position, weighted by how likely the particle is to be found there.
It's like a weighted average then, where the wave function tells us how much each position contributes.
I think I'm following, even if the math itself is a bit fuzzy right now. But why is all this important? What's the point of calculating these expectation values? That's the key takeaway here. Expectation values let us physicists make predictions about quantum systems. Because even though we can't be certain where a single particle will be, expectation values help us predict the average behavior of lots of particles.
So we're saying, well, we may not know what one particle is doing for sure, but we can still understand how these systems behave as a whole, right? And that's what allows us to even build technologies that use these bizarre quantum principles.
Precisely. That's the beauty of expectation values. They bridge that gap between this probabilistic world of quantum mechanics and the world we see every day, and they are essential for understanding so many things, from how atoms work to the semiconductors in our electronics.
Wow, it's amazing. I'm starting to see how important this concept really is. But so far, we've just talked about position. What about other properties, like a particle's momentum? Is that calculated similarly?
That's a great question, and that's where things get even more interesting. But we'll dig into that next time. So before we jump into momentum, I think it's good to remember that Expectation values, right? They give us a handle on how, on average, many particles behave when they're all prepared the same way. And it's not about measuring a single particle repeatedly, but more like the statistical distribution across a whole group of them. This is important because it lets us actually predict something, even in a realm that seems to be, well, governed by pure chance.
Exactly. It's kind of like we're saying we can't know for sure where a single electron is headed, but we can predict how a beam of electrons will behave, on average.
Exactly. Now, to your question about momentum, it's calculated using a similar approach, but with a little twist. Remember how we mentioned that every measurable quantity in quantum mechanics has an operator?
Yeah.
For position, it was pretty simple. We just multiply the wave function by x, the position coordinate.
Right, because we're basically asking what are the chances of finding this particle at position X?
Exactly. But momentum is a bit more abstract. Its operator uses something called a derivative, which tells us how the wave function itself changes over space.
Okay, I vaguely remember derivatives from calculus. They're all about, like, slopes and rates of change, right?
You got it. So the momentum operator isn't looking just at the value of the wave function at a single point. It's looking at how steeply it's rising or falling as we move along that x-axis. A rapidly changing wave function means the particle has a higher momentum.
Oh, okay. So, like, if the wave function is like a rolling hill, a really steep hill would mean high momentum, and a gentle slope would mean a smaller momentum.
That's a perfect analogy. And just like with position, to get the expectation value for momentum, we use the sandwich method again. Operator nestled between the wave function and its complex conjugate, integrate over all positions, and there you have it, the expected momentum.
Okay, I'm definitely working to visualize all of this, but it's really neat how the wave function's shape itself tells us about both the particle's position and its momentum.
It is quite elegant, isn't it? And it really highlights a deep connection between a particle's motion and the spatial properties of its wave function.
Now, going back to that probability cloud idea, we said the particle could be anywhere, technically, but it's just really unlikely to be far away from where it's most probable. Does that apply to momentum too? Could a particle, in theory, have a, like, crazy huge momentum, even if it's extremely unlikely?
That's a sharp observation. And you're right, in theory, the wave function goes on forever in both directions, so the possible range of momenta is technically infinite. But just like with position, the probabilities for those really extreme values get super tiny.
So it's like saying, yeah, I could win the lottery, but I shouldn't quit my job just yet.
Exactly. We usually focus on the range of momenta, where those probabilities are, significant, as that's where we'll get the most useful predictions.
That makes me feel a little better. I was picturing particles, like randomly zooming off at the speed of light. So we've talked about position and momentum. Are there any other things in the quantum world we can calculate expectation values for?
Oh, absolutely. Pretty much any measurable quantity you can think of, energy, angular momentum, spin, they all have a corresponding operator we can use with this framework. It's a pretty powerful tool, really. It lets us make sense of so many different quantum phenomena.
So even though individual events in quantum mechanics might seem totally random, these expectation values give us a way to, like, tame that randomness and actually understand how these systems behave.
Precisely. And that's what makes this concept so important. It bridges the gap between this bizarre probabilistic world of quantum mechanics and the more predictable world that we experience in our daily lives.
This all leads to a bigger question, though. If we can only talk about probabilities in quantum mechanics, does that mean there's a limit to what we can truly know? It's a question that's, like, puzzled physicists and philosophers forever, hasn't it? If all we can really talk about are probabilities, does that mean we just can't ever fully know the quantum world? Like, are our tools just not good enough, or is it something deeper?
You've hit on one of the, one of the most mind-boggling things about quantum mechanics. There actually is a fundamental limit to how precisely we can know certain pairs of quantities at the same time. And it's not that our tech isn't good enough. It's really baked into reality at the quantum level,
See, there were the things we're just, like, fundamentally blocked from knowing for sure no matter how hard we try.
Exactly. The most famous example of this is Heisenberg's uncertainty principle. It says the more precisely we try to measure a particle's position, the less we can know about its momentum, and vice versa, of course.
Okay, I need a visual here. Help me understand why that would even, like, happen.
Sure, imagine you're trying to pinpoint where an electron is. To see it, you got to interact with it somehow, right? Like shining a light on it.
Yeah, that makes sense. Got to detect it somehow.
But here's the thing. The very act of, like, interacting with that electron, say with a photon of light, it messes with the electron's momentum. It's kind of like, well, imagine you're trying to measure how fast a tiny feather is moving, but you do it by throwing a baseball at it. The harder you try to see where the feather is, the more you knock it off course.
So it's not that our measurements are clumsy, it's that the measurement itself is changing what we're trying to look at.
Exactly. It's a deep consequence of this quantum world we're talking about, and we just can't get around it. This uncertainty is just, well, inherent.
Hmm. Does that mean the electron doesn't actually have a definite position and momentum until we measure it?
Right.
Or is it more like it does have these properties, but they're hidden from us until we force it to pick one with a measurement?
That's the million-dollar question. And it leads to, all these different interpretations of quantum mechanics. Some theories say that particles don't have definite properties until they're measured. Others say they do have them, but they exist in this fuzzy, probabilistic state until we make a measurement.
Like that tree falling in the forest thing.
Right.
Does it make a sound if nobody hears it? We're getting philosophical here.
It really is profound. It's one of the things that makes quantum mechanics so fascinating. It forces us to think about some of the deepest questions about, like, what reality even is. But even with this uncertainty, it doesn't mean we don't know anything, right?
Right. That's where those expectation values come in again. They're like a framework for making predictions,
Yeah.
We can understand the behavior of these systems, even if we can't know every single thing about them with, like, perfect accuracy.
Exactly. They're the key to navigating this strange world where uncertainty is just everywhere. We can extract real info from that probabilistic dance of those quantum particles. We can't know everything, but we can still make sense of it.
This has been, wow, a real trip through the quantum world. I feel like I understand more how physicists deal with this realm of probabilities and all this uncertainty. It's mind-bending, but also super exciting to think that the universe works so differently at that level.
It's truly captivating, isn't it? And honestly, the more we explore, the more we realize just how much more there is to discover.
Well, thanks for being our guide through all of this. Definitely made my brain work, but in a good way. Until next time, everyone.